Okay, so hello everyone. My name is Sawon Kim, and I'm a PhD student in mechanical engineering at MIT. And today I'm going to present uh, my research that I've done in previous recent years. So the title is the model-free tracking control of a fiber drawing process using deep reinforcement learning. So as the title suggests, I developed a deep reinforcement learning method that can be applied to the fiber drawing process. But not only the fiber manufacturing, this method can be implemented to many other manufacturing processes. So I've done this research during my master's with my advisor, Dr. Brian Anthony. Also, this work is under the revision at the IEEE Transactions on Mechatronics. So the thermally drawn fiber is widely used in telecommunications, optical imaging, and making fabrics. So to begin with, let me briefly explain how the fiber drawing process works and what methods are used to control the system. So the figure on the left shows a typical fiber drawing system. So first you feed in the preform to the furnace where the material is heated near the melting temperature. Then the material is pulled from the furnace to generate the thin fiber. And after that, it goes through the cooling and coating process, and it finally accumulates on a spool. So the most critical requirement for the process is to keep the fiber diameter to a desired set point. So therefore, there has been a lot of effort to develop a controller for regulating the fiber diameter in both industry and academia. So most of the fiber drawing process in industry utilizes the PID feedback control. So for example, we are recently collaborating with a company called Sterlite, one of the largest optical fiber manufacturer, and they also utilizes the PID feedback control with some gain scheduling in order to regulate the fiber diameter. And not only in the fiber manufacturing, but the PID controller is so popular that according to a survey, 97% of regulatory controllers in chemical industry utilizes the PID feedback. There also has been some model-based approaches where they come up with some model and use the model for advanced control. So for example, there has been work that uses state space modeling and applying the linear quadratic control. Also, some work has focused on developing more realistic reduced order models. And there also has been some works on CFD simulations to reproduce the neck down profile and the temperature distribution of the fiber. Um, However, there are like several limitations to these approaches. Like one limitation is that the controllers are tuned and modeled only around the nominal set points. In other words, the controllers are only valid around that nominal set points. So therefore, it cannot be used when we try to modulate our reference trajectory or when we try to change our set point from one to another. So of course, it would be great if we can come up with some model that can address those dynamical transiences. However, modeling the transients between one set point to another is much harder than modeling only around the nominal set points. This is because we have to consider all the physical dynamics that happens during that transitions. So if modeling those dynamics behavior is hard, our question is, can we come up with a model-free method for a dynamic control of processes that are hard to model? For example, let's say that we want to regulate the fiber diameter to track this varying reference diameter trajectory. If we use the PID control, it will result in some delays and overshoots. Also, the model-based controllers that were mentioned before are not applicable since they are only modeled around a fixed set point. So is there any other way that we can regulate these like varying fiber diameter while not requiring any process model? If we can come up with this method, there are several advantages. First of all, we will be able to produce fibers with more customized geometries. For example, we could make a fiber with a wavy profile, as you see in the top left figure, and extend this to make the customized fabric. We could also extend this approach to vary not only diameter, but also cross-sectional patterns in the future work. One other point that I would like to emphasize is that this method can also be implemented to other similar types of processes. The same framework can easily be extended to other processes like 3D printing, food processing, or maybe chemical engineering. So if we would like to develop such controller, what are the main requirements? As I implied at the previous slides, the controller should be predictive and it should be model free. So first, if the controller is not predictive, for example, like PID controllers, it will cause some delay in response. The delay becomes a problem when the reference trajectory is changing fast, especially for the systems that have a delayed dynamics. This lack of predictiveness is critical to the tracking performance. And if we look at the fiber drawing process, the process involves significant delay dynamics. So for example, if we change the feed rate of the preform, then the response in diameter will show up several seconds later. Therefore, if we just use the PID control, the tracking performance will be very poor. The next requirement for the controller is that it should be model free. So for the model-based controllers like LQR, linear quadratic regulator, and MPC, the model predictive control, the performance of the controller depends on model accuracy. However, as mentioned before, the fiber drawing process is very hard to model accurately, especially when we try to modulate our diameter. So we need to consider all the physical phenomena like rheology, fluid dynamics, heat and mass transfer, and etc. So therefore, while we could still come up with a model from first principles, the performance may not be satisfactory. Therefore, our proposed controller should not require any prerequisite model about the system. So based on these requirements, let's evaluate some of the conventional control methods. So first of all, the PID feedback does not require model. However, it is not predictive. And the LQR is not predictive and also it requires model. And the MPC is predictive, however, it requires model. So therefore, in order to overcome these limitations, we are proposing a deep reinforcement learning-based controller. So the proposed controller can predictively control the system, and also it does not require any explicit model about the system. Rather than requiring the explicit model, the controller will learn how to control by directly interacting with the system. So our proposed method is based on deep reinforcement learning, which is one subsection of machine learning. So for recent years, we experienced exponential growth in computational resources. And following that, many research has been done using machine learning and reinforcement learning. So the deep reinforcement learning has outperformed humans in various games, like, for example, AlphaGo, and it has been used to solve some physical task simulations. Also, it is very widely used in research communities of robotics and autonomous driving. And machine learning is also used in manufacturing research, and they are usually focused on data analytics or cost, quality, and anomaly predictions. However, not much work has been done using not much work has been done in real-time manufacturing process control. So therefore, I hope that my research derives many following research towards these directions in manufacturing research communities. So before we move on to the main part of my presentation, let me summarize the main contributions and features of my research. The main contributions of my research is the development of a process control system that does not require analytical or numerical model can predictively track various types of reference trajectories and can be implemented to real-time manufacturing processes. And we used deep reinforcement learning as a methodology. Then this control system is deployed to a compact fiber drawing system that we developed in our lab, as you see in the left figure. Just to tease out some results, our proposed method outperformed PID and MPC in terms of tracking performance. The figure on the right bottom shows one of the example results. So our controller, so DRL model, and the PI feedback and the QDMC, which is a type of MPC. So these controllers are used to track this sinusoidal reference trajectory. And our proposed controller is compared with a PID controller and a QDMC controller. And you can see that our proposed controller has less phase error and amplitude error than other baselines. So my presentation will have the following outline. So far I talked about the motivation, and from now on I'll briefly explain about our compact fiber drawing system hardware. Then I will explain how we implemented our reinforcement learning algorithm, and then I will show you some of the results. And finally, we will conclude and discuss about the future directions. So
just a quick point, Sang-Moon. So all of you heard yesterday Chris Couch talk about how he was implementing a real-time control system for complex manufacturing, continuous manufacturing. And so this is a very, very similar problem. And Chris wouldn't tell you the secret sauce of how it all worked. And Sang-Moon is now going to give you an example of what the secret sauce is and how he actually, in this case, how he has solved this problem. So just wanted to kind of reference back to yesterday so you could understand we had the industrial problem coming from Chris, and now academia are presenting a solution to that problem. So sorry, Sang-Moon.
No, I think that was a good point. So yeah, as Bruce just mentioned, I think this is one example of like how machine learning or reinforcement learning like algorithms can be actually implemented to real-time time series manufacturing process control. So I think that was a very good point. Thank you for mentioning that. And yeah, so let me just continue. So yeah, so as mentioned in the previous slide, so we deployed our control method on this compact fiber drawing system. And this device was developed by David Kim, one of our co-authors throughout his PhD. So typical fiber drawing tower is like several meters high. And this compact system is a miniaturized version of those towers with only 50 centimeters high. And it has all the major components that a typical fiber drawing system has. So first, it has an extruder system where it heats and feeds the preform into the system. And after that, the fiber is drawn from the extruder, and there's a laser micrometer that measures the fiber diameter. And lastly, it has the cooling system and the spool system to cool and store the produced fiber. So this system takes several control inputs and measures several outputs. So as the control inputs, it takes spool voltage, preform feed rate, and etc. And as the measured output, it measures the diameter of the fiber and spool speed, and etc. So based on these inputs and outputs, our controller will regulate the fiber diameter. So now let's move on to the implementation part of the reinforcement learning. So before we do that, I think we need to know what is the reinforcement learning. So the reinforcement learning is a method that trains a software agent to maximize a cumulative measure of reward. So how it does the training? So it trains the agent from the interaction with the environment, which in our case, the manufacturing process. So let's say there is an agent, the controller, and the environment, the manufacturing process. So first of all, the agent will execute the control actions based on this control policy. And also a noise is also added to this action to enable exploration for a good action. Then, as a consequence, the environment will be affected and it will return the observed state and the corresponding reward. And lastly, the agent will improve this control by reinforcing the high reward action. In other words, by the reinforcement, the agent will tend to take actions that are similar to the actions that resulted in higher reward in the previous data. So this is why we call this method the reinforcement learning. So now we know the basic idea of the reinforcement learning. So let's dig into more details. So this is the overview of how our algorithm looks like. And we use the specific approach called the actor critic. And as the name suggests, it uses two components called the actor and the critic. So the actor is the controller that interacts with the system, and the critic is the one that evaluates the actor's action. So the idea is that the actor improves its control to get a better evaluation from the critic. So let's look how it works in step by step in the next slides. So first, let's look at the actor. So the actor is the agent that controls the environment. It takes the measured observations from the environment and computes the control's actions accordingly. If we take a closer look, then it looks like this. The actor, the DRL agent, takes the reference diameter and all the measurements from the environment, like measure diameter and measure velocity. Then it computes the extruder's feed rate and the spool motor's duty cycle. Then these control inputs are exerted on the system, and the measurements such as diameter and velocity are fed back into the DRL agent. So as the controller interacts with the environment, it will generate the history of the measured outputs and input actions. And from those informations, we can also compute the reward. So for example, in our case, the control objective is to reduce the error between the reference trajectory and the measured diameter. So therefore, we use the negative value of the diameter error as the reward function. Then all of these informations, the measurements, the actions, and rewards are stored into this history memory. So now let's look into the critic side. As I said, the critic is the one who evaluates the actor's action. So it should learn what is the good action and a bad action. I won't go too much into the details on how it works, but the main idea is that the critic samples the previous data from the history memory and learn by looking into those data. So as the critic learns what is the good and bad action, next, the actor tries to improve this policy by getting better evaluation from the critic. That is called the actor update. In summarize, the critic learns how to evaluate by looking into the previous data, and then the actor learns from the critic on how to get the good evaluation. So now let me explain how we train these networks. To train the controller, we input the reference trajectory with some random step changes. The reason we use the random steps rather than just one single step is because we want our controller to address the nonlinearities to the step sizes and step locations. So let's see how it worked out. The x-axis is the time in seconds, and the blue line here is the reference trajectory with the random step changes that I just mentioned in the previous slide. And the red line is the measured diameter. And at the bottom, we have our input actions. The light blue line is for the motor's duty cycle, and the pink line is for the preformed feed rate. So this figure shows at the very beginning of the training process. So since the agent hasn't learned anything yet, it just takes some random exploratory actions. And you also see that the diameter is very unstable. And this is how it looks like after 15 minutes of training. You first notice that the diameter is less unstable. And we can see that the controller is trying to do some modulations. For example, we see that the extruder input in pink is high when the reference diameter is also high. However, it still suffers to track the reference accurately. This is after 1 hour and 14 minutes of training. So diameter is much more stable, and now the controller does more elaborate modulations to track the reference trajectory. So for example, if you look at this part, so you see that the controller, so this pink line is taking steps several seconds ahead of this reference change. So you see this slight several seconds of gap between the steps in inputs and steps in outputs, so that it can like predictively track the reference. So as a result, this is how the learning curve looks like. So the x-axis is the training time, and the y-axis is the root mean squared error of the diameter. And as a baseline, we compared our DRL method with PI control and the QDMC method, which is a type of MPC. So as you can see from this curve, our proposed method outperforms PID feedback less than in 1 hour and achieves a comparable performance with that of QDMC within 3 hours. Yeah, so now we have our trained controller. So next what we should do is, so we're going to test this controller on various types of reference trajectories and see how it works for each of these varying reference trajectories. So these will include the random step changes, which we used for training, but also it includes some continuous trajectories like sinusoidal signal or some smooth splines, which were never faced during the training process. So first, we tested our controller on this single steady trajectory at around 550 microns. And as expected, all of the PI, QDMC, and DRL performed reasonably well, and there were no significant difference in performance. However, for a mass conservation model, which is an open loop model, it showed this downward trend. So this is because the fiber stacks around the spool and makes the effective radius of the spool larger. And due to this increase in the effective radius, the linear speed of the fiber increases, and the open loop controller cannot compensate that, so that we see this downward trend. And next, we tested on the random step changes. So the PI controls showed some overshoots and delays. And in contrast, the QDMC and DRL showed not much overshoots and performed reasonably well. And as I explained earlier, the DRL predictively controls by modulating the inputs in advance. Next, we tested on a sinusoidal signal. So as I mentioned, we used this continuous step changes when we trained the DRL. So therefore, the DRL controller, our proposed controller, has never faced these types of continuous trajectory. So can it be generalized to track these continuous trajectory as well? So if we look at the results, seems like the answer is yes. So the QDMC and DRL performs reasonably well, while the PI shows some overshoots and delays. So that was only at a single frequency of the sinusoidal signal. Then what will happen if we increase the frequencies? How fast can each of the method track the reference trajectory? In order to answer that question, we tested on the sine sweep signal with gradually increasing frequency. So this is sine sweep signal, and you see that the frequency is gradually increasing as the time goes on. So as the frequency increases, all of the controllers show this increasing trend in RMSE. And this is obvious because there is a physical limit on how fast the system can respond. So eventually, all the controller won't be able to track the reference if the frequency is too high. So yeah, then let's compare each method at the rest of the frequencies. So first of all, the PI showed the highest RMSE, and the QDMC and DRL, the red line and the green line, performed similarly under the lower frequencies. However, at a higher frequencies, the DRL had an edge over the QDMC method. So this table summarizes all the results that I showed so far. So when the reference trajectory is simple, for example, in a steady trajectory, all of the PI, QDMC, and DRL performed similarly. However, the DRL starts to stand out as the trajectory gets more complicated and difficult to track. For example, when the trajectory involves random step changes, or when the frequency or amplitude increases in the sine sweep trajectory. So this means that the DRL enables more customized geometry of the fiber, and also it implies that it will enable more complex operations when applied to the other similar processes. So that was our main results, and the conclusions is as follows. So we developed a process control system that does not require any analytical or numerical model and can predictively track various types of reference trajectories and can be implemented in real-time manufacturing processes and by using the deep reinforcement learning as a methodology. Then we implemented on a compact fiber drawing system. And as a result, the proposed method outperformed other baselines, especially when the reference trajectories are difficult to track. And we expect that this will enable more elaborate process in fiber drawing and also other similar processes. So there are many interesting future directions. So for example, in order to reduce the time for training, we could pre-train the agent with the existing data instead of training from the scratch. Also, we could try to boost the training speed by combining it with the conventional controllers like PI controllers. On top of that, there are 5 projects in our lab that is going on that were derived from this research. So with the SDL, the Sterlite, we are developing a simulation model using a similar architecture. And also with the IMA, Nissan, and Dow, we are looking into the other types of processes that we can possibly deploy the similar approaches. And lastly, with the Liberty Mutual, we're developing a method to apply these types of methods on the encrypted data space. So that's it for my presentation today, and for the rest of the time that we have, I'm happy to answer any questions.